Hey guys, welcome back to Pop 'em Up Chem. This is going to be the first video of Unit 3. We're going to be looking at the periodic table and how we can use the periodic table as a tool, really, and then take a quick peek at some of the physical trends of the elements on the periodic table. So I've got to start a question that's a little bit different than normal here. I want you to have a look at these two sets of shapes and this test shape. So this test shape either fits in set A, this one, or set B, this one, or neither. So can you work out which one it fits into, and preferably why? Pause the video and have a go at that. And the reason I've chosen this is because this is all about pattern recognition, which is the fundamental underlying process that we're investigating in this unit, periodicity, patterns in chemicals. But we can think about pattern recognition more broadly as well. So if you saw that the test shape has half of the sided shapes are coloured black and half of the sided shapes are coloured white, you could have also used the corners, that all matches with set A, where half of the shapes have black and half of the shape have white, which is unlike set B. This is actually a question from a UK CAT exam. Some of you may have already heard of that. If you're applying to medicine in the UK, that's a type of assessment that looks specifically at different types of reasoning, like this. So this is where it all started, or at least the start of what we call the modern periodic table. This is Dmitry Mendelev's periodic table, and you can see he's included the common groups, elements that we know are there, and he's also included gaps for spaces left because he knew that there was elements that had not been discovered yet. So this is the progenitor of what we call the modern periodic table. You could see that, and this took him a couple of decades to make this. You can see he's structured things by mass and also grouped things by the way they react. And that's still what we do in the periodic table today, except we've had some developments since when this one was made. So these developments include important things like the discovery of the proton, which is obviously the basis of the sequential organizing of the atomic numbers on the traditional periodic table that we've seen and used before, the number of protons. We also have the relative atomic mass, which is the protons plus the neutrons. We still have things grouped by the way they react. However, this traditional periodic table is not the only way we can organize it. Firstly, we could put the F block elements in their place and in the sequential order, the lanthanides and actinides. We don't usually do this because formatting is a little bit more difficult. You can see it's a little bit harder to view the individual characters than if we condense it and move these out. They're also often studied quite separately from a lot of the other elements on the periodic table. The Janet periodic table specifically organizes the elements by how full each of their atomic orbitals is, and this is commonly used by physicists, still organized with the same grouping as in the traditional periodic table, however. And this is actually commonly used by physicists. However, some periodic tables move away from this style of grouping altogether, like the Benfey periodic table, and this was created to show the increasing energy levels of the atoms. While it does still keep the group coherence, you can see the group 1 running up the center, it also has these spaces for the transition metals, lanthanides and actinides, and even a hypothesized and as yet unproven stable set of theoretical superactinides. Other periodic tables, such as the Stowe periodic table, has sought to emphasize the kind of beautiful, if you like, symmetrical nature of the principal quantum numbers, the amount of elements at each of these quantum numbers increasing and then decreasing. This is actually a 3D graph, and you can see in the bottom right hand corner the key for navigating it in 3 dimensions. Others, like Ziemeczynski, attempted to do the same thing, representing the symmetry of the principal quantum numbers. And my personal favorite, the Jaeger periodic table, would have been a 3D representation. I think this would actually make a really wonderful model to actually have on a table, but I've never got around to making one. But here you can see that the different orbitals are represented off different axes from this central plane and still grouped in the same reactivity patterns. So it's important to recognize that even in the sciences, the way that we present information can drastically affect how they're interpreted. And this is exactly what you look at in TOK. The periodic table is a great example of this. Depending on what we want to use it for, we may use a different periodic table. That doesn't necessarily make one right or wrong. They're all models. What's important for the IB course is that you know the anatomy of the traditional periodic table. You know your way around it, you know how to read it, and you know how to use it as a tool. We have 2 main planes on the periodic table. They are the groups. These go down the periodic table, and we have the periods, which go across the periodic table. The groups are labeled across the top of the periodic table, 1, 2, 3, or sometimes called 13, 14, all the way up. Going down the periodic table, we have the periods, 1, 2, 3, 4, etc. And the position on the periodic table tells us quite a lot. These groups 1 and 2 through 13 and 18, or sometimes 3 to 8, these are called the main group elements. These are group 1, 2, and 13 through 18. Now, group 3, proper 3, all the way up to group 12 are the transition elements. And although you won't see it on the periodic table in your data booklet, there is a rough line dividing the metals and non-metals, which kind of goes down in a stepwise fashion from between boron and aluminium all the way down, with the metals being to the left-hand side and to the right-hand side being the non-metals. The line is not fixed, however, and many of the elements that lie along the side of these lines have properties of both metals and non-metals, and we call those metalloids. At the bottom we have the lanthanides and actinides, but we don't pay particularly strong attention to those in IB. Not only that, but it's so well organized that the groups all show similar chemical properties, and the periods show changing properties as we go across, and these changes in properties actually form trends, and we can have a reliable periodization, hence periodic table. And that's the beauty of the design of this. It's organizing all of these things to tell us so much information. We really can use the periodic table as a tool. Indeed, we should think of it as a tool. And the important components here are the electron configurations. We know that all elements in the same group have the same number of electrons in the outer shell, in their valence shell. And we know that all of the elements that are in the same period have the same number of electron shells, or the same principal quantum number. What does this imply? Well, it implies that as we go down a group, the outer electrons are going to be further away from the nucleus. This may seem obvious, of course they're going to be further away from the nucleus. The atoms are larger because they have a higher principal quantum number. But this also means that those outer electrons are going to have less electrostatic attraction to the nucleus, and that has huge implications on lots of different physical and chemical properties. And most of this effect of the reactivity as we go down the group happens due to the fact that larger atoms are going to find it easier to lose electrons because less attraction to the nucleus, and conversely, larger atoms will gain electrons less easily as new electrons will have less pull from the nucleus. And this relationship underpins so many of the trends we see in the periodic table. Couple of questions for you then. As you go down the group, it is what to gain electrons? Pause the video. Pop them up! As we just said, as you go down the periodic table, the atoms get larger, which means less attraction to the nucleus, so it's going to be harder to gain electrons. Next, all the elements in the same group have... Pause the video. Pop them up! Of course, number of electrons in the outer shell, the same number of valence electrons. Next question, as you go up a group, valence electrons are what to the nucleus? Pause the video to have a go at that. Pop them up. Of course, as we go up the group, the atoms get smaller, and so the valence electrons become nearer to the nucleus. Really, this should all sound pretty familiar from effective nuclear charge, which we covered in Unit 2. Remember, effective nuclear charge is the charge felt by the valence electrons, taking two things into consideration: the distance from the nucleus and also the shielding of other electrons. We can calculate this Z effective as Z, which is the number of protons in the nucleus, or the total number of electrons, minus S, the non-valence electrons. We can envision this with 3 electrons here, 1 valence electron and 2 shielding valence electrons. We have attractions between all of the electrons and the nucleus, but we also have a repulsion between the shielding electrons and the valence electrons. So the balance between this attraction and repulsion is given by the equation for effective nuclear charge and helps us understand how tightly the nuclei is going to hold on to that outer electron. So remember, Z effective or effective nuclear charge is going to increase as we go across the periodic table, because we're not going to be increasing shielding electrons but increasing protons, but doesn't really change that much as we go down a group. Their distance becomes the main effect of the attraction between the nuclei and the valence electrons. So let's look at the trend of atomic radius. So firstly, we can define atomic radius, and this is given by half of the covalent bond distance between two nuclei. And we can kind of see this as an atom's size. The reason we use this measurement is there's no simple measure of an atom. If we think about the orbitals, they're kind of fuzzy and the edges aren't defined. So this is a way that we can have a more consistent measurement by using half the covalent bond distance. We measure this as given in the data booklet in picometers. So picometers are meters times 10 to the minus 12, so very small measurement. And there are two main factors that affect this. Obviously the principal quantum number, because that's the number of shells, and of course the charge of the nucleus, which references effective nuclear charge, how much the nucleus pulls those valence electrons in. And we can look at ionic radius, which is much the same measurement but for ions, as we might expect. It represents the size of an ion and is measured in a similar way to the atomic radius. The important thing to think here is that we're not dealing with atoms, so we have to remember what happens when we add or take away electrons. So we have two options. We can either remove electrons for an atom or add them. And in every single case, when we remove electrons, the ion is going to become smaller And that's because we're removing electrons, so there are less electrons to repel each other and make the atom larger, so we have a smaller ion. And the opposite is true when we have a negative ion. If we add electrons, we increase internal repulsion of the electrons and the ion becomes larger. So positive ions are always smaller than the parent atom and negative ions are always larger than the parent atom. We measure this in the same units as atomic radius, so it's also in picometers, which is, remember, 1 × 10⁻12 meters. There are two main factors that influence this, and you have to be a little bit more careful when you're thinking about this. The first factor is, of course, the number of shells, the principal quantum number. And the reason you have to be careful is this can change from the parent atom if we remove electrons to go down to the next energy shell, for example. Also, the charge in the nucleus and how much that pulls on the electrons will also affect the size by pulling the outer electrons in more or less. We also see trends in the periodic table with the first ionization energy. We looked at this in Unit 2. Remember, ionization energy is the removal of 1 electron from 1 mole of gaseous atoms. And we see a periodizing effect here. We see an increase as we go across the group, from group 1 to 2. Then we see a decrease as we go down periods. And then we see a general increase across. And for a more detailed discussion of why we see the different permutations as we go across the group, you can check out the video in Unit 2. But there are two main factors at play here again: the effective nuclear charge and the number of shells, the principal quantum number. These factors are dictating a lot of these trends, as you may have noticed at this point. And the unit we use for first ionization energy, hopefully you remembered, is kilojoules per mole. So looking at electronegativity, and if at this point you're getting bored of me explaining these trends because you know the things that are going to be governing why they occur like that, that is a good thing. It's a good thing that you're understanding the principles of periodicity. So remember, with electronegativity, we have the most electronegative in the top right and the least electronegative in the bottom left of the periodic table. So we see an increase from left to right as we go across the period, and we see a decrease as we go down. Remember, electronegativity is the tendency of an atom to pull a bonding pair of electrons towards themselves. The same factors are influencing electronegativity, right? Across the group, we see increasing effective nuclear charge, and down the group, we're seeing increasing distance from the nucleus, which is why we're seeing a decrease in electronegativity down the group. Now, we haven't discussed electron affinity before in Unit 2, but electron affinity is the energy released when 1 electron is gained by 1 mole of a gaseous atom. You could think of it as the opposite of ionization energy, or first ionization energy. Now we have a similar trend to that of electronegativity, where we see an increase generally across the period, and we see a decrease generally going down. And same factors, the size, so we see an increase in electron affinity up the group, and of course we're going to see the charge, the effective nuclear charge, influence as we go across the period, so we see an increase in electron affinity as we go across the periodic table. However, just like ionization energy, this isn't a smooth increase across the periodic table. We actually see a peak in group 2 for electron affinity, because adding a new electron to a group 2 element would mean adding an electron to the unfilled 2p orbitals. So just like with ionization energy, the orbitals are influencing the general trend. So the peak we will see will be in group 2. This is of course apart from the noble gases. So the last trend I'm going to look at in this video is the melting point. So this is the temperature in Kelvin that an element melts or turns into a liquid, kind of obviously at this point. Now, this doesn't have the same kind of predictable trends that we've seen in our other trends, and that's because so much of this is based on bonding, and that's why we did Unit 4 before Unit 3 in class, and those videos will be up soon. And in Unit 4, we discussed why a giant covalent or a simple covalent or a metallic bond may have a higher or lower melting point. And although there are some trends within those in the periodic table, they're not completely reliable because different elements bond in different ways. So the strength of the bonding, the number of other atoms it's bonded to, the type of bonding, strength of intermolecular forces for our simple covalent compounds is also really important. So when we think about melting points, there's less of a general trend apart from when we look at group 1 and group 7. So the group 1 and group 7 or 17 elements allow us to employ the trends and properties that we know the periodic table shows us to have a look at what happens with melting point. So in group 1, we see that as we go down from lithium to sodium, potassium, etc., we see a steady decrease in the melting point. And the reason we see a steady decrease in melting point is because all of these nuclei get successively larger because they have a larger principal quantum number, which means the outer electrons are further away from the nucleus and less tightly held, and therefore they are able to be pulled apart easier, or less energy is required to do that, thus giving us a lower melting point. In group 7, we see a trend. It's a different trend and for a different reason. Indeed, we see it increasing down the group. In fact, we see fluorine and chlorine as a gas at room temperature, and we see bromine as a liquid at room temperature and iodine as a solid at room temperature. So we see a steady increase in the melting point, and that is to do with our intermolecular forces that we covered in Unit 4. As we go down the group, as you'll know, we increase the number of electrons. As we increase the number of electrons in each molecule, that is more electrons that can contribute to London dispersion forces and therefore increase the force of attraction and therefore increase the melting point. So quite a few properties and trends for us to take in this video, but always bringing it back to those same reasons that we started to look at in Unit 2 and also using knowledge from Unit 4 to explain them. There's a lot to remember, but if we remember the underlying principles of how to use the periodic table as a tool, then we're going to be able to illustrate why we see these periodic trends using structure of atoms and bonding instead of just rote memorization. Let's do a couple of questions to test it out. First question, are the ionic radii for negative ions larger or smaller than their parent ions? Pause the video, give yourself a moment. Pop them up. Of course, for negative ions, we have added electrons. It's going to increase the repulsion inside the atom, and so negative ions will always be larger. Give 2 factors affecting atomic radius. Pause the video. Pop them up. Hopefully you got bored of me saying these for both this trend and the others. It's going to be the charge on the nucleus, or the effective nuclear charge, and of course the principal quantum number, or the distance the outer electrons are from the nucleus. Okay guys, there's some questions uploaded on this and a task that focuses more on interpreting data to deduce these trends than just regurgitating them too. Once again, thanks for joining me. Don't forget to like, subscribe, hit the bell icon, and as always, Practice makes slightly better.